If you look straight up at noon on a clear day, the sky is a brilliant blue. But just a few hours later, as the sun drops toward the horizon, that same sky bleeds into vibrant shades of amber, crimson, violet, and deep gold. The sun itself hasn't changed. The air you are breathing hasn't suddenly morphed into a different substance, yet the atmosphere completely transforms its palette. This daily transformation isn't just a aesthetic luxury, it is a direct, visible map of atmospheric physics in real time. To understand why the sky changes color at dusk, you first have to look at light itself. The light streaming from the sun appears white, but it is actually a blend of every color in the visible spectrum. You can see this whenever sunlight passes through a glass prism or through droplets of rain to form a rainbow. Each color in that spectrum travels as a wave, but they don't all travel in the same way. Colors like violet and blue have very short, tightly packed wavelengths. Colors like orange and red have much longer, wider wavelengths. When this mix of sunlight enters Earth's atmosphere, it collides with billions of gas molecules, mostly nitrogen and oxygen. These molecules are extraordinarily tiny, much smaller than the wavelength of visible light. When light encounters particles this small, a phenomenon called Rayleigh scattering takes over. Rayleigh scattering states that shorter wavelengths of light scatter off small gas particles far more efficiently than longer wavelengths. In fact, blue light scatters roughly 4 times more effectively than red light. At midday, when the sun is directly overhead, sunlight enters the atmosphere at a steep angle and travels a relatively short distance through the air before reaching your eyes. During this brief trip, the long red and yellow wavelengths pass straight through without much interruption. But the short blue wavelengths get struck by nitrogen and oxygen molecules and bounced around in every direction. When you look up at the daytime sky, you're seeing that scattered blue light arriving at your eyes from every corner of the atmosphere. So why doesn't that scattered blue light stay around for sunset? The answer comes down to pure geometry and distance. As the Earth rotates and the sun descends toward the horizon, the angle of incoming sunlight flattens out dramatically. Instead of plunging straight down through a thin slice of atmosphere, the sunlight must now travel horizontally through a vastly thicker cross-section of air. At the horizon, sunlight travels through up to 10 times more atmospheric mass than it does at high noon. As that sunlight treks through this long, dense corridor of air, Rayleigh scattering keeps happening over and over again. The short blue and violet wavelengths are scattered so many times in so many directions that they get dispersed long before the light reaches your eyes. They are essentially filtered out of the direct beam of sunlight. What survives this long-distance journey are the resilient, longer wavelengths, the yellows, oranges, and deep reds. They pass right through the dense air without getting scattered away, painting the sun and the surrounding sky in warm tones. This filtering effect is also why the setting sun appears dim enough to look at briefly without blinding glare. The dense atmosphere acts as a giant pair of natural sunglasses, stripping away the intense high-energy blue light. But Rayleigh scattering is only half the story behind the most dramatic sunsets. The atmosphere is rarely just pure gas. It is filled with aerosols, microscopic particles of dust, sea salt, pollution, smoke, and volcanic ash. These particles are significantly larger than gas molecules, often comparable in size to the wavelengths of light itself. When sunlight strikes these larger particles, it undergoes a different process called Mie scattering. Mie scattering doesn't favor blue light over red. Instead, it scatters all wavelengths relatively equally and mostly in a forward direction. When the air is rich with fine aerosols, Mie scattering takes the already warm red and orange light coming through the horizon and spreads it out into a broad, glowing haze. This is why dusty desert landscapes or areas downwind of wildfires often produce the most intense, fiery sunsets you will ever see. Clouds add the final dynamic layer. High-altitude clouds like cirrus or altocumulus act as natural screens hanging in the sky because they are elevated. They catch the direct, red-shifted rays of sunlight long after the ground below has slipped into shadow. The bottoms of these clouds bounce those rich red and pink wavelengths down to the surface, creating sweeping visual canopies that shift in intensity by the minute. Ultimately, a sunset is a reminder that the air above us isn't empty space. It is a dense, fluid blanket that actively filters and bends cosmic light. Every time you watch the horizon turn to fire, you aren't just watching the day end. You are witnessing millions of miles of solar radiation being stripped, scattered, and sculpted by the very atmosphere that keeps us alive.